Hi everyone, I'm Xavier Jeremia, account manager at Dyze Design. So welcome to our webinar on high-flow extrusion 3D printing. So thank you for registering and joining. I'd like to quickly introduce you our two presenters. Simon Duchaine and Philippe Carrier are two of the co-founders of Dyze Design, which specialize in developing hot end extruders, sensors, and other kinds of accessories that control supply and deposition of raw material in material extrusion 3D printers. So the products improve the reliability and usability of 3D printers and enable materials to be printed, thus empowering people to manufacture the tools and objects they need, where and when they need them. So Phil serves as a Chief Technology Officer and has more than 6 years of experience designing state-of-the-art extrusion systems. And Simon serves as Chief Commercial Officer. So we will have a question and answer session at the end of this webinar. So I would invite you to submit your question using the Q&A tab, and we will follow up at the end of the presentation. All that said, so I'd like to hand over to Simon.
So thank you, Xavier. So here's a bit outline of what we'll talk today. So first off, we'll talk about just a bit an overview of the additive manufacturing industry. Then we'll cover what's material extrusion. Then give the landscape of industrial material mix printing. And then we'll go in the core of the webinar, which is high-flow 3D printing. And finally, we'll have our Q&A session. So without further ado, let's talk about the additive manufacturing industry. I know for sure that some attendees are already pretty familiar with the industry, but we can still cover some topics for newcomers and give some common ground as well for the upcoming topics. So in the last few years, it's no surprise that 3D printing is gaining more and more ground in the manufacturing field. Every year, engineering companies are continuing to see the benefits of 3D printing, not only for prototyping, but increasingly for end-use parts. At the moment, 3D printing is primarily used for prototyping. However, aesthetic or functional end parts are not really far behind that. And this same trend is also echoed by the amount of 3D printed part produced in one order, with the majority of engineering businesses creating from 1 to 10 parts per production run, suggesting they are mainly used for prototyping and testing, with other manufacturing processes like injection molding used for mass production. The cost of the tooling for injection molding, or really any other traditional manufacturing processes, being quite high, 3D printing is a really appealing process for small production runs due to the cost per unit being almost always the same, yet quite low for the first tens of units. So even if 3D printing is gaining more grounds, there are still some barriers to implementing 3D printing in industries. The principal reason being the high initial cost of additive manufacturing, but also the quality of printed parts not being good enough. And one interesting barrier is the general perception that material choice is too small. We'll see later on, but this is specifically those aspects that can be solved by using what we call high flow rate 3D printing technology. Also, beside the barriers of adopting 3D printing, the actual additive manufacturing users generally want a better and bigger portfolio of 3D printable materials, but would also want more reliable technologies and more sustainability. So when it comes to the additive manufacturing industry, there are mainly 7 technologies. Material extrusion, vat polymerization, material jetting, binder jetting, powder bed fusion for polymers and for metal, direct energy deposition, and sheet lamination. I won't go and explain each technology, but I simply wanted to state that the webinar today will be focused solely on the material extrusion technology. In fact, to note, still today, material extrusion is still the more common use technology, both by in-house manufacturing departments, but also by external services like 3D printing services companies. So that's what leads us to talk in more depth about the material extrusion technology, commonly known as a fused filament fabrication, fused deposition modeling, or fused granulate fabrication. There's still a lack today of standardization regarding the naming conventions, but we generally prefer to talk about MEX or material extrusion rather than using each terms that are referring to subtype of the material extrusion technology. So what's material extrusion? In short, it's a process where a raw material is taken, here on the slide, in the form of a plastic filament, but sometimes it could be powder, pellets, or even paste. And that material is fed through an extruder, a mechanism that is moving the material to a melting zone. In this example, the extruder is a pinch system grabbing the filament and then bringing the material in the melt zone, sometimes called a hot end, and deposited through a nozzle on a surface to create a shape layer by layer. In material extrusion, different types of material can be used. The most popular being polymers, but metal is also possible with material extrusion technology, as well as ceramic. And in more exotic applications, you could see bioprinting or even food printing. Finally, there are different subtypes of material extrusion technology. So on the left, it's the plunger base, where you are using a syringe or a pump to generally extrude paste or clay or biomaterial and any fluid-like materials. The middle one is the filament-based extrusion, the most common type in the industry, where you are using a polymer or a composite filament and driving it through a geared extruder. And then finally, there is the screw-based type, where you use for powder or pellets. And basically, it's a motor that is turning an endless screw to move the material all the way through the melting zone. All that said, let's go to the second part of that webinar. But before diving a bit deeper in our main topic today, about basically high flow rate printing, let's just take a few moments to go over the different types of 3D printers being used nowadays in industrial applications and see why high flow extrusion is a critical factor when it comes to small production runs. So let's dive a bit more in each printer segment and see basically the pros and cons of those printer types. But please take into account that it's basically our own segmentation here, as there is yet no official segmentation. Some would provide a different different printer types based on printer costs, other on the material type, things like that. Here we decided to segment based on basically the form factor, or rather the build volume of the overall machines. So the first one is the desktop 3D printer. It's a good pick for printing small parts with high resolution. The extrusion system is generally made to print layers and shells with a nozzle of 0.4 millimeter, making the surface finish almost not visible. In the case of the desktop printer, having a high flow extrusion system isn't necessarily critical. You could still get reasonable printing time for larger pieces, but as an indicator, it would basically take about 500 hours to completely fill the build volume of, let's say, a Prusa printer, where we would have 0.3 millimeter 8 and 0.4 millimeter width shells. The second one is what we like to call the industrial 3D printer. basically it's a mid-sized machine from 0.5 meter to 1 meter build volume. Unlike most desktop machines, it can take high temperature material or any advanced material due to the heated environment or abrasion resistant components. Generally, it's a bit more reliable as most of the time the industrial 3D printers are using better quality components. However, they are somewhat costly and you need expertise to operate those kind of machines. For those mid-size printers, considering a high-flow extrusion system might be a good idea. Using the same indicator than the desktop printer, we calculated that it would take 6,500 hours, so about 8 months, to completely fill the build volume with a desktop format extruder. It's basically 13 times longer than a desktop printer. The final type is the large format 3D printer. It's all in the name. Those machines are designed to print big pieces all in one part, or actually multiple pieces on the same machine. If you're looking for high resolution pieces, it actually can do it, but generally you'll pick that kind of machine for printing bigger parts where resolution isn't the main goal. You'll use nozzle size like 1.2 millimeter and print bigger shells. Problem is that most of the time, the extrusion system used on those machines is inadapted for a large format. As an example, using the previous indicator, it would take more than 36,000 hours to completely fill the build volume with a desktop format extruder. With a large format 3D printer, using a high flow rate extruder is really critical.
Cool. Now let's cover the core of today's presentation, high flow rate 3D printing. High flow rate doesn't necessarily mean high movement speed. Building a part faster can consist of layering thicker layers on a regular 3D printer that isn't designed for tremendous acceleration and travel speed. There are many advantages into thicker layers, both for the machine design and the part strength. I'll start with the filament-based high-flow extrusion and then follow with the pellets-based high-flow extrusions. One way to increase profitability is using a high-flow or high-output filament extruder. The extruder throughput is the limiting factor for printing speed, where a printer can easily move the carriage faster than the extrusion system can deposit the material. Using a high-flow extruder removes this bottleneck, each printer being able to make a 3D printed part faster. There are already a few solutions on the market, each with their own advantages and disadvantages: E3D Supervolcano, 3D Platforms HFI, and our own Typhoon extruder. Typhoon is described as a high flow and fast print all-in-one extrusion tool head specifically designed for industrial large-scale 3D printers. This print head is designed to extrude 2.85 millimeter filament, is compatible with standard firmwares, and is capable of delivering an average flow of 200 cubic millimeters per second, which is about 0.9 kilogram per hour. This means quicker print at high deposit rate. High flow isn't all about volumetric flow rate. It's also about constancy. An extruder like the Typhoon has a quad drive system for a reason. As you can see on the graph on the right, both single drive and dual drive systems suffer from a drop in efficiency the faster they go. It translates to inconsistent line width through the print. It's harder to obtain precise dimension when the throughput isn't predictable. This is the reason why the Typhoon has 4 driving wheels for fast and predictable flow. If we compare the Typhoon to a standard hot end like our Dyze X, we see that about 6 to 10 times faster flow. Both extrusion systems are using the biggest nozzle available to them. We can also see that the Typhoon throughput scales much better with the temperature, thanks to the dual heating and longer melting zone. We advertise the Typhoon as 200 cubic meters per second, but that's an average flow rate because, as you can see here, the Typhoon can reach a bit more or less depending on the specific material you're printing, the amount of heat required to melt, the viscosity, the added fillers, and the coefficient of friction are parameters that affect the maximum output flow. Each heat core can be switched easily with a knob turn, removing the whole heat core rather than the nozzle prevent any leaks or problem from the end user manipulation. The abrasive-resistant nozzle prevents any changes in nozzle size and height during a large print with abrasive filaments. Sizes are available from 0.6 millimeter to 2.5. Here's the widely common print test we did, a benchy at 925% scale. The big benchy took only 18 hours to print. Printing such part with a regular extruder considering 200 microns layer and 70 millimeter per second printing speed, it would have taken about more than 120 hours, which is 5 days, about 7 times longer than with a Typhoon, for a print that ends up being only half the weight. So in brief, here are the benefits of a high-flow filament extrusion. As we've shown with the benchy boat, you can greatly increase your productivity by reducing the print time. To reach high deposition rate, the Typhoon is a well-adapted solution for any big-scale 3D printer. It doesn't need special printer with super fast-moving axis. And with the easy swappable nozzle from 0.6 up to 2.5 millimeters, the Typhoon can be adapted to any situations. Now let's talk about the Pellets extruder. It's another good way to increase profitability in material extrusion. An extrusion screw is able to melt polymer much more efficiently, thus can reach much higher flow rates. Using pellets has another benefit. The cost of raw material is on average 8 times lower when using virgin resins and even lower when using recycled polymers. Here are some high-flow extrusion systems available on the market. You have the CEAD pellet extruder, massive dimension, and our own pulsar extruder. There are a lot of different pellets-based systems out there, all with their own specific maximum flow rate, weight, and size. The choice of a system will greatly depend on your maximum payload. Generally, the bigger the size, the higher the flow rate. The Pulsar is a state-of-the-art, large-scale and high-flow plastic pellet extruder. It was designed with one purpose in mind: 3D printing of parts of 1 cubic meter and more as quickly and cost-effective as possible. The Pulsar is compatible with any large-scale 3D printer and robotic arms and is able to output on average 2.5 kilograms per hour of material. The customized screw design is optimized for 3D printing with high resolution. The screw is manufactured in-house using heat-treated alloy steel and then coated for an optimal wear resistance. The triple heat zone design ensures the polymer is at the right temperature at the right place. The top section receives cold pellets and generates more heat to melt them. Then, the middle zone stabilizes the polymer and at a precise temperature. Finally, the nozzle heater ensures an even flow. Pulsar can be used with nozzle size of 1, 3, and 5 millimeters. Blank nozzle drawings also can be provided for customized sizes. Nozzles are made from tool steel with a wear-resistant coating. As the screw can't pull molten plastic, an anti-oozing mechanism ensures nice-looking prints without any flaws. Combined with wiping, the same result as a traditional 3D printer can be obtained. Similar to the Typhoon, the flow rate depends on the material you're trying to extrude. With PLA, for example, the Pulsar can reach up to 3.3 kilograms per hour or 7.5 pounds per hour. One interesting thing about a pellets extruder like the Pulsar is how fast you'll be profitable. Let's take an example of a PETG. A 1 kilogram spool costs about $35 per kilogram, while 1 kilogram of resin is about $8 when bought in small quantities. After only 130 hours of printing, you have basically made your money. You basically save more than $60 per hour by using the pulsar rather than a filament extruder. Pellets are very easy to acquire. Even if you need small quantities, there are many suppliers such as Chase Plastic, NatureWorks, and Push Plastic. They can provide resin in bags starting at 1 kilogram up to a ton if you want. Resin also can be bought from other distributors and usually are found in 1,000 kilograms, and the price is even more advantageous. We can also provide automatic pellet feeding system to get the pellets from the container to the extruder, and standard pellets dryer can be added to the feeding loop when the resin is hygroscopic. So in brief, here are the benefits of high-flow filament pellet extrusion. The pulsar is actually 3 times faster than the Typhoon, which is again a great solution for big parts that needs to be printed in a record time. The pulsar is highly weight optimized and has a throughput to weight ratio 3 times higher than the closest competitor, which makes it ideal for a robotic arm where the payload is a critical factor. When printing parts that requires dozens of kilograms of polymer, saving on the raw material makes sense. As we've shown previously, the pulsar would pay itself after a few hours of printing.
All right, thank you, Phil. So now Simon and Phil will answer some of your questions. Can you tell us more about the robotic arm?
Yes, Phil, I can take that question. And I see in the chat that Peter is asking almost the same thing. So let's cover that topic. So the pulsar with a 7 kilogram of weight, I think can be implemented on almost the smallest robotic arm you can find on the market, even small cobots like universal robots. And basically, it's quite easy to integrate using the provided stepper motor driver and the provided solid state relays. All you need to have is some kind of controller that can output direction and steps for the motor, and then to have some kind of temperature PID to control the heaters. Beside that, one thing to note is that, as we've shown on the picture, you have some kind of heat shield around the pulsar. It might makes it harder to have, let's say, wide angles when you print, and basically that's a question of Peter here. So we plan, and we're working right now on having what we call the non-planar version of it. So it's an iteration of the same design where we will add some clearance around the nozzle to make sure that you can print at different angles when you rotate it with a robotic arm. We still have some customers right now printing with robotic arm, but as I said, because of the clearance, you can't really do the maximum orientation you could reach with a non-planar version. But we're working on that right now.
Thank you. We got another question. How you prevent clogging?
I can answer this one because I've worked a lot with William, which is our expert at Dyze with the pellet extruder. So clogging, I think the most common cause for clogging is what we call a bridging at the top of the screw. So it's always, let's say most of the time, it's caused by the wrong temperature settings. So if your top section is too hot, and most of the time, if you take the data sheet for a standard extrusion process, meaning you have a much longer screw and you have more heating zone, the first zone are usually pretty hot for our application. So most of the time, to prevent clogging, you have to reduce the temperature at the first heater to make sure that the pellets won't be melting too soon and stick to the screw, so that they can progressively melt to the point where they won't clog because they will be pushed by newer pellets at the top. So the temperature settings is mainly the cause of clogging. It's very easy to avoid.
Thank you, Phil. Another question, what new updates, features can we expect on Typhoon and Pulsar in the future?
It's a good question. As Simon said, we've been working more and more with people using robotic arms. So one thing we've worked on is developing solution that enables a wider angles, clearance angle for these products, so that the robotic arms can use them at much wider angles and make complex parts. Also, I see that Peter was talking about feeding the pellets when the extruder is inverted. So right now we still rely on gravity to bring the pellets in the screw. So sadly, if the gravity won't bring the pellets to the screw, there won't be any extrusion. It's not something we've planned on because we haven't had so much request about using it upside down, but there's quite a wide range of angles that can be used, as the entry is still at 45 degrees. So it can work under certain angles without too much trouble, but definitely, sadly, not upside down.
Okay. Is this possible to clean the nozzle during the printing?
I think during the printing, the cleaning process, you can have two different types of cleaning. You have the wiping, which usually consists of moving the extruder over a brush. Then if there's something that is stuck on it, will be cleaned by the brush. Otherwise, if we speak about the pulsar, cleaning the nozzle usually implies using a purging compound, which usually has something that is not abrasive, but let's say it has glass fibers inside that will scrape the internals and make sure that there's not any more traces of the polymer that you were extruding. So it's usually done manually. So during the printing, it could be a challenge to switch and clean the internals of the nozzle, but the outside of the nozzle is usually much easier to do.
Thank you, Phil. Yes, Simon?
Yes, I can take the next question. And it's a good question, actually. So does Dyze have a turnkey printer solution available? So basically, Dyze Design isn't a 3D printer manufacturer, but we are providing extrusion system to basically a 3D printer brand. So here, I think in the attendees today, there are different companies that are partners. So those companies can offer the Typhoon or the Pulsar in some of their machines. So we can send you a list. We have different partners, but I think today in the attendees there are like Filament Innovation, 3D Platform. Basically, we're working with also manufacturer of bespoke printer like Compound Dynamics or I don't have all the lists in my head, but basically, if you want to have turnkey printer solution, you can always send us an email at sales@dyzedesign.com, and with pleasure, we'll provide a list of different partners based on your requirements for a printer.
Thank you. Has anyone used Typhoon or the Pulsar on any printer bigger than Filament Innovations Kraken?
Yeah, the Kraken is quite, I think, the biggest printer I ever saw using the Pulsar and Typhoon. So I'm not sure. There might be, because we sold the Pulsar and Typhoon to different end users and customers, and some of them might have built a custom machine for their applications, but I'm not aware of actually a bigger printer than the Kraken.
Actually, something that is commercially available.
Yeah.
All right. And another question, do you hold data on processing PA6?
Yes, we do. Recently, we started giving as many information as we can in our documentation section. So both for the Typhoon and the Pulsar, there is a new section in the slicer settings, which is the speed, where we provide the, for example, the flow rates you can expect depending on your configuration with the nozzle size. So it should help you determine the proper speed for your print settings. I think when it's outside of the extrusion, for example, bed temperature and all of that, we suggest checking the filament details. But as far as printing speed, we also have our calculator, which can help. And we have some formulas and example which using our flow rates, you can find the proper speed for your print. So you won't have to try and error a couple of times before finding it. You should be fine using it right away.
Thank you, Phil. We got another question from Chen. What can you say about tungsten carbide nozzles with abrasive pellets?
We've seen a lot of abrasion with small nozzles, for example, 0.4. Those are very critical for abrasion because it seems like the wear effect are more intense. But as soon as you start getting into something bigger, like 1 millimeter, 3 millimeters, we could not see any wear in the nozzle. So we decided to keep tool steel because it's easy to machine, it's easy to get. We don't have to pay mold fee. And the reason is we haven't measured any requirement of going into something that is more intense, more wear resistant than the tool steel for the bigger nozzles. So it was perfectly adequate for the Typhoon and the Pulsar.
Thank you, Phil. We got another question. What are the challenges in extruding carbon fiber and polymer pellets?
Actually, the question should be reversed. It should be, what are the challenges extruding virgin pellets? Because with carbon fiber, even when you go in a higher density of fillers, because with the filament, usually you are restrained to something that is close to 20%. Otherwise, the filament will break. But with the pellets, you can go much higher. But the added fillers will make it easier to extrude. So usually when we do extrusion flow test, everything that has wood fibers, carbon fibers, fiberglass fibers, everything that is not a pure virgin polymer will extrude faster. And also the shrink rate is much lower when you have fibers. So actually printing with carbon fiber and polymer is the easiest polymer to print with, because once you put it on your bed, it's not going to shrink or warp. It's going to be very precise in terms of flow because it's easy to extrude. So the extrusion system is not that much struggling compared to, for example, polycarbonate. This one has, I think it's one of the polymer that requires the highest torque for extruding. So a virgin polycarbonate is much more stressful for the extruder than anything with carbon or glass fibers.
All right. We got another question from Sean. Can your extrusion systems operate at elevated temperatures for enclosed printing?
It's a good question. So the whole thing is water cooled. So we've designed it to be able to maintain itself in a reliable temperature. The thing is, it always depends on the carriage design and how everything else is set up, because most of the time the connectors are the thing that are problematic for high temperature. So everything that is mechanical is well contained, and the water makes an amazing job into keeping the whole thing cool. However, if the connectors are not kept in a in a cooler environment, so protected from the hot chamber, these parts can become the problem.
Thank you, Phil. Did you try printing with metal injection molding feedstock with pulsar extruder? And can it be done to print large metal parts?
Yes. However, the current screw, we call it the universal screw because the one we provide is kind of a general usage one. We've seen that the MIM, since they have a very low content in resin or in wax, or depending on what kind of MIM feedstock you use, it behaves very differently from the polymers, meaning that the screw is not, it's able to extrude it, but you are not able to get a constant line width. It's going to change depending if it's been sitting there or depending on the speed. So it's able to extrude MIM, but the result is very inconsistent.
Thank you, Phil. I got another question by email. What are the requirements to get started with the pulsar and the Typhoon extruder?
Usually you need a 3-axis machine. Can be a router, can be something you've made yourself. When you have that, all of our documentation will guide you step by step into wiring and then firmware settings. We have a couple of examples. So definitely, if you want to go that way, I suggest a minimum of knowledge into the 3D printing with a smaller printer first, because it's basically very similar, just into a bigger scale. But the Typhoon and the Pulsar have been designed to replace a very standard extruder. So the way we've chosen the temperature sensor, the way we decided to go with something that is very simple system, so there are no controllers that you need to interface by any means. It's just raw sensor and raw heaters and raw motor signals that you manage. Then it's much easier to integrate into different solutions that way.
Thank you, Phil. Can an high-flow big nozzle system handle a polymer with longer fibers, effectively making it carbon fiber, not carbon stubs? It's a question from Bjorn.
That's a very good question, actually, because we've never been able to get our hands into long fibers chopped. So usually we have the regular stuff that is provided with the standard resins. I think the material with the biggest chunks that we've managed to print were polypropylene with pine wood, and the pine wood were not powder, but they were literally like chips of wood, and when you were extruding them, you could see the chips kind of getting away from the resin. So I'm pretty sure that the slightly longer fibers could be working fine with the Pulsar, because there are no filters, or in standard extrusions they have more layers and mixing zone. The Pulsar is very straightforward. It's a compression screw, and then you have the anti-oozing and then the nozzle. So there are not that many constraining zones. So I think pretty big stuff could pass through.
Thank you. Do you have plans for a continuous fiber extrusion system?
Right now with the Pulsar, we don't have any plans for that. I know that there are a lot of patents that prevents us from using certain solutions. So right now, I think we're still working on a simple extrusion.
Okay, thank you. What are the challenges for reliable and consistent extrusion on the Pulsar?
It's a very good question, because even though we've managed to get good results. I think one of the major challenges is that every polymer will be much different and will need more tweaks. So in the slides, I've talked about the wiping, but there's also parameters like the pressure advance. So the Typhoon, if you push the filament by a certain amount of distance, you know that you have exactly this amount of polymer that will go out. It's one-to-one. But with the pulsar, the screw is not 100% moving the filament. It's actually building a pressure. So you have a kind of lag when you start the screw and when you stop the screw. And every polymer will have a different lag. And most of the firmware have something that is called the pressure advance, which will tend to compensate this lag. So it will start by over extruding and it will stop sooner than it should to let the pressure release. So it's a little bit of a challenge. If you plan to have like perfect parts, you need to put a bit more time into fine-tuning all of these parameters in order to get the extrusion to go and stop when you want it to. But once that is nailed down, usually you can put as many resin as you want from the same type of resin, and you'll have good results.
And I must insist also on the care of the polymers. So for sure, if you sit different polymers there without, let's say, drying them or putting desiccant in your bag, moisture will grab in the polymer, and then you'll have some inconsistency because of that. So pressure advance and tweaking your parameters and your profile with good care of your polymer, I think it's the good way to achieve a good aesthetic for let's say pellet base printed parts.
All right. Could the pulsar be adapted and able to perform desktop injection molding in aluminum and resin castings? And how many grams does the complete chamber hold?
Sadly, there's a difference between extruding screws and injection molding screws. So the injection molding screws will fill a chamber, the screw will move back, and there will be some kind of a blocking mechanism, a locking mechanism that when the screw is pushed, it acts as a piston. So the pulsar has no means of doing that. It's an extrusion screw, and it's not able to generate a lot of pressure because since we are always printing in free air, the goal of this extruder is not to fight, is not to try to fill a mold and put a lot of pressure in the polymer to make sure that every little hole is filled. So we've managed to reduce the screw height and thus reduce the weight of the system by lowering the pressure output of the system. So definitely, we've never tried it, but I'm pretty sure that it would not be able to fill a mold properly.
Thank you, Phil. What percentage of CS reinforcements do you recommend for pulsar for constant printing?
So far, we've tried mostly 30 and 20%. We haven't seen much difference in printing both of them. It's hard to say on the long term what are the differences, but as soon as you start having a bit of fibers, it's already a good start if you want to have something that is easy to print.
Thank you. We got another question from Sean. What is the suggested control system firmware for best leveraging your extrusion systems?
So far, we work a lot with Duet 3D. So it has a lot of features. It's very clean implementation of the heating zones. So you can have all of them associated to a tool, which makes it more clear and you can also rename them, so top, middle, bottom. So all of those small details makes it easier for the end user. Whereas if you are using Marlin, which is more popular with the desktop printers, you won't have all of these features of combining the heaters. And so the end user has to know that T0 and T1 are this heater or another one. So in terms of user experience, I think the Duet is worth the extra bucks you'll put in it.
Thank you, Phil. I think we're done with the questions.
All right. So
I think that Chen asked what's the length of the pulsar.
Oh, yeah.
It's actually 484 millimeters. And if you want, on our website, if you reach the page, you can have access to 3D models. So if you want to see if it fits, you have access to a step file, drawings, and all the technical details about the product we sell.
Any plans for an even smaller pellet extruder that can be used on smaller printers?
It's a good question. It's something that we are asked a lot, because a lot of people were customizing the nozzle to get something smaller. So definitely it's something that we are evaluating, and maybe someday we'll release a smaller version of the pulsar.
Thank you, guys. Cool. So if there's no question, I mean, we still have 10 minutes, but we oh yeah, new questions. Cool.
Okay, the Duet 3D, is that for the pulsar, or will it also help if you have a Typhoon?
So the Duet will work with both of them. It's able to handle the heaters and the temperature sensor for 3 or 2. So both of them will work with the Duet.
Because something that we can say is that in the Typhoon, you have 2 independent heating zones, and on the Pulsar, you have 3 of them. So basically, in your control board, like Duet, and in your firmware, it's like if you're mimicking using, for the Typhoon, 2 extrusion system, and for the Pulsar, it's like if you were implementing 3 extrusion system on your machine. So basically, that's the way that Duet is managed, and the firmware is managing it, is that each heating zone is an independent tool head, and that's where you can change the temperature. And as Phil said earlier, in our documentation, you can see for the top, mid, and bottom one, what's the best temperature to input based on your material. So it seems complicated, but if you read the documentation and do a documentation, you'll find out that it's quite easy to set up.
All right, we got 2 another questions. Can it be used in a bulk printer setup, and can it be used underwater?
Regarding the belt printer setup, definitely it can. And with the work we're doing on the high clearance nozzle, it should be even easier, because right now you might need to tweak a little bit the shroud around the nozzle to get able to put it at an angle. But definitely with the next version, let's say the configuration will be offering for the non-planar printing, you'll be able to print on a belt. And regarding underwater, sadly, there's a high risk of electrocution, and none of our parts have been designed for printing underwater.
Another question about the Typhoon and the Pulsar. What drive system, belt, lead screw do you recommend?
We recommend something that is rigid. Sadly, most belt will have tendencies of vibrating caused by the high weight of the extrusion system and the acceleration you want to have on your printer. So a lead screw is something that is good, and also other alternatives that are more rigid than belts could be evaluated. We have seen some printers using rigid chains for moving certain axes when they are quite long. So it's something that could also be interesting.
Thank you. We got a question from Mike using the Pulsar. So when tuning PID on Pulsar, I'm getting an error. I guess it's a different heat zones. Should I hook them up in series instead?
No, the heaters should definitely not be wired in series, because you will lose the control you have on individual zones. I believe if you have errors, it sounds like it's something about the Duet. I know that the Duet, with the latest beta version, they have greatly improved their error managing with slow heating and heavy heaters. So I know that in the past they had protection that either it was heating too fast or too slow, and a lot of our clients had problems with the PID tuning. So we strongly suggest to contact Duet team and check with them how they can prevent those safety features that are not optimized for high flow and high power heaters.
Thank you. Do you have plans for button setup, including high flow hot end?
Right now, we don't have any plans for the Bowden setups. There are a few reasons behind that. For example, the Typhoon is able to push about 20 kilograms of force. And this is something that we've worked hard to make sure that there won't be clogs and we can reach high flows. The thing is, when you start working with Bowden and you have something that can push 20 kilos, the PTFE tubes and also the fittings that are holding them are becoming the bottleneck. So in the past, we've seen a lot of the teeth inside the fittings that were broken because the Typhoon was too strong for the fittings. So also, usually we prefer having something that is direct drive, even though the weight is a little bit higher, because the end result is much better. We haven't had a lot of requests about getting a Bowden for something that is high flow. I know that any printer that is optimized for speed would want that, but I feel like it's not the kind of way we've chosen when we started working on the Typhoon.
Thank you. We got a question for Simon. Is there a special discount today for Pulsar Typhoon orders?
We didn't actually plan to give a discount code today, but for sure, reach out to me, reach out to our sales team. If you attend the webinar today and you're interested in the Typhoon, in the Pulsar, we can check your particular use case and provide pricing based on your request, and because there's a lot of things to consider when it comes to the Typhoon and Pulsar. We have some add-ons we can provide. So basically, each account manager will go through an offer with you and make sure that everything that you have everything on hand to be not plug and play, but actually to implement that in your machine.
But make sure that you have listened well to this webinar, because we'll ask 5 questions, and the more right answer you have, the higher is the rebate.
We got another question from John. Does that mean you can run a Typhoon fully on Marlin if you set it up like a dual hot end setup?
Yeah, exactly. So you'll be heating T0 and T1, but never send any extruding commands to the T1. You'll be always working only with T0. The T1 will be simply keeping the temperature stable for the tip of the nozzle. So it's a setup we have currently on 2 of our printer. Actually 1, because we transferred 1 printer to Duet, but we still have 1 running on Marlin.
Thank you. We got another question from Sean. Do you have non-thermoplastic large extruders, for example, photocured resins?
No, sadly, we were very specialized into thermopolymers, so we don't have anything that is, we don't have any solution for mixing and curing.
All right.
So we're 4 minutes to the end of the webinar. So let me just check. All right. So if you have any more questions, don't hesitate to basically send us that by email. I'll write in the chat where you can reach us. So simply write an email at sales@dyzedesign.com, and I'll be able to take the ticket, or our account management team will reply to you, or at least refer to Phil or me, and we'll be able to answer all your questions. So thank you everyone for attending today, and it was our first webinar, and I'm sure we'll put up some more in the future.
If you'd like to hear more about a specific subject, we'd be happy to listen to your comments. Thanks.
Thank you.
Thank you, everyone.
Thanks.